you want to read it? You see the picture?
We can see the picture.
Okay.
So we are presenting from. Okay. Should I go ahead?
Yes, go ahead there now, please.
Hello.
It's all in your hand.
Okay. So this. Okay. This is a physiochemical and microbiology analysis that we did at the Water Research Institute together with my colleagues here, Sada Tu and Salom Bobo. And we are here to share with the result at the Ghana Space Science Center. So that is what you are seeing on your screen. So we go to the next slide. And okay, the next slide is a quotation from our very first president who established the GAEC, the Ghana Atomic Energy Commission, and that was a powerful quotation from him. He said, "We have been compelled to enter into the field of atomic field energy because this already promises the greatest economic source of power since the beginning of man. Our success in this field will enable us to solve the many-sided problem which we all face in all the spheres of our development as a nation, that's Ghana and then Africa. And we are seeing it with what we have on our hands with the nanoparticles, the Gans, what it can do. And it is always, fascinating to hear, to see the expression on the faces of people. Nash is here with us. He can testify. Yesterday, somebody was miraculously, or I would say it is just instantaneous. His hand was pinning him. I was called, and then I came in and then I did what I know to do. And he said, if the way my hand is moving continuous like this, then I'll be at the work tomorrow because I've been going to the hospital for about 2 weeks now, and they are giving me the same treatment, and I'm not responding. And he said, I'm going to carry your message across. So it already promises a lot of the atom power and the science of nuclear technology, if properly applied, has answer to every answer to our many-sided problem, like our first president said. Next slide.
Okay.
Next slide, please. Okay. The Water Research Institute.
Benjamin, before
Yes,
you go further,
yes,
you have to explain the work which is done by Benjamin and Atomic Energy Commission has brought in interconnection with the governmental research lab with water. That's why you see one part of the government, which is the Atomic Energy Authority of Ghana, has seen the work of the cleaning of the water, and now they transfer the knowledge to the Water Research Institute. That's how we are going inside the governmental work. We show one, and they transfer the knowledge to another department to benefit the nation. This is how the Keshe Foundation will grow across the world, internally within the governments. Carry on, please. Hello, Benjamin.
yes, sir.
Okay, carry on, please.
Okay, so we are, like Mr. Kesh rightly said, we are liaising with the Water Research Institute in this area, and the Water Research Institute is part of CSIR, that is a Council for Scientific and Industrial Research, which is made up of 13 research institutions. so it's big. And so if you have one problem and you cannot solve it, you move to the other end. Like I was doing a test with Sada here, and we came across the problem with sediment, and he said, no, let's go to this side, and she has taken the sediment there for analysis. So if it comes to electronics, they are there. It's a big institution. So, and this was the Water Research Institute was formerly, known as Institute of Aquatic Biology Studies, but they merged with another institution called the Water Resources Research Institute. So WRII of the CIR, which was established in the 1960s. So it's an old establishment, and so they are very knowledgeable when it comes to water. And if you get to their labs, you can see what they are doing. Different, applications, research going on in terms of water. So they are doing a lot of things. And each and every time I go there, I'm so fascinated with. I know that I don't know anything about water, so they know much more about water here. Please, can you get to the next slide? So we were doing it this way. As you can see on your screen, we were doing it in big containers, and we're just pouring the what do you call it, the Gans in, and sometimes it was even in the west state, and we couldn't measure it because uh, it we need an experiment should be able to be repeated by anybody anywhere at any time, and it should give you the same, what do you call it, results. So we're like doing it, but it was not, properly documented. So that was our first experiment, my first experiment with Sada. And I mean, some of the water settled properly, others didn't settle well. So we sat down, and then we decided to see how we can improve the efficacy of our results. So we decided to go from the micro level, then we can go to the macro. So that's the big scale.
Pardon? Am I-
Hello?
Benjamin, could you
Yes, sir.
explain to us, the people who are with you, what's the qualification in the institute?
Okay.
What is the position?
Okay. Let me leave for them to do. Sarah, please, can you introduce yourself?
Um, Hello, good morning. I'm Sada Mohammed from the Water Research Institute. If you could kindly repeat what the question you wanted to ask,
We
Benjamin.
would like to know that what we collaborate with each other. What is your position in the institute? What's your education background that you follow these tests? That we understand.
Um,
Do we want to show people there instead of the screen share
Please.
for a minute?
Yep,
Okay.
please. You go on camera so we can see your beautiful face.
thank you, thank you. Mostly the people there are mostly researchers and technical people. Our educational background is from HND and first degree in the lab. Then we have others with masters and PhD. So mostly we do a lot of water related collaboration. We work with Danida, FID, um, a lot of Royal Chemical Society. When it comes to water, we work with most of the donor agencies a lot. Mostly they tell us which projects they want to do. We look for a technical and competent person to lead the project from Ghana, and we do correspondence. Mostly that is what we do.
Okay. And you are the person who analyzed the water.
Um, yes, and my background is chemistry, BSc chemistry, MSc, pharmaceutical analysis and quality control. I'm with the environmental chemistry division of Water Research Institute.
Thank you very much. Dealing with qualified people, highly qualified in your field. We respect your opinion and what you teach us. Go ahead.
Okay.
It's good to know who we are dealing with in so many ways that we can
Okay.
face to the voice and to the knowledge. Thank you very much.
Okay.
Okay.
Thank you too.
Yeah,
Hello,
thank you.
I can give it to his colleague also.
Hello.
In the camera, he gets excited, so we'll take. Okay. Can you introduce yourself, please?
I'm Salomubo from Microbiology Section of Water Research Institute. My background is molecular biology and biotechnology. So I do most of molecular work and microbiological work at the Water Research Institute.
And your qualification? What's your background in the
Molecular biology and biotechnology.
biotechnology? Thank you very much indeed. So we see what you can offer, because the information you give us today will be passed on to a number of governments around the world. You have tested things very methodically. I've seen your reports in the background. I'll see them when they come in, when Benjamin sends it. And it's amazing how, as I said, Africa will lead the space technology through the work of people like you. So if you can explain to us the reports and how we can go ahead and learn from you in the coming weeks and months on a regular basis. We rely on your input to learn, so you become the leaders in the knowledge with the space technology and gas and the water. So thank you very much for bringing your knowledge to us.
You're welcome.
Thank you very much.
I'll continue with the slides. So
Please.
please turn over to where we got to, and then I can continue from there.
Okay. Rick, go back to your section, please. Okay. Now we see you see what we see, the containers.
So these are the containers. We started with these ones, but like I said before, we were just taking it and doing it anyhow because the efficacy of the guns proved to be very effective. But as scientists, sometimes they ask a lot of questions. How many grams? How many? The weight of it, the quantity and all that. It must be verifiable. So we decided to, take all this into consideration and go the proper way and do it in measured steps. So that's how we, started. Please, the next slide. So one of the reasons for refining the technique was that an experiment should be able to be replicated at any time. If you cannot replicate an experiment, then it suffers from what is called pseudo replication, and you can read it from the ecological monograph of Hubert, 1984. So it's not just what we are doing. It's not something that just happened randomly. We are doing something that can be replicated at any time because water problem is all over the world, and as the slides rolled on you, I will tell you what is happening currently this week, what happened on the radio and in the news media. So please, the next slide. So these are some of the principles and guidelines that we stuck to in order to get a good result. Okay, so for a successful experiment to take place and be repeated anywhere, these steps are necessary. We plan our procedure, and then we got our samples properly, and then we prepared our samples, and then we did what do you call it, performance and analytical procedures, and then we took time to record everything for statistical purposes and measurement. Please, the next slide. So, in order to remove the salinity from the gans, because one of the she did it whilst I was doing it with Nash. Sada was also doing it, but the salinity of the Gans at that time was very high because of uh, um, me not getting access to uh, good distilled water. So I just applied it. But when I went there, they have a lot of things. So I mean, we what do you call it? Wash the Gans properly and then remove the Gans because the reason why we use somebody was asking me the other day why is it sometimes salty, and I was telling the person to get the Gans, this is the medium that you use salt. You use salt and two dissimilar metals, one a nanowire and then the other, depending upon what you want to produce, you immerse it, and then so the salt, the Gans get trapped in the salt. Because the Gans is already a free plasma, you cannot wash it or what do you call it? Take desalinate it and then free what do you call it? The Gans for other applications like power generations and so on, and for health and then water treatment applications. So that is a step, an extra step that I worked on with SADA, and we were able to get it right. And we took off the salinity of the Gans before applying it. So that's a plus. Please, the next slide. Okay. So one of the steps we also took was when the Gans is wet, you cannot measure it because it's not a dry matter, and we don't know the content of moisture. We don't know the amount of moisture that is trapped in the Gans. So the first thing we thought of was also to dry it and dry it properly, because working with dry matter, otherwise known as dry weight, is a measurement of mass of something which is completely dry and is usually preferable. Okay, because you can know the actual what do you call it, the weight of the Gans that you are using, so that you can record it. As we roll the slide, you see why it's necessary. So we use a coffee filter to what do you call it, coffee filter paper, to actually dry it, and then we dry it at room temperature, and then that was it. Okay, next slide, please. The next step was taking the proper weighing procedures, and in doing so, we what do you call it? Use the Adam analytical skills. These are very good skills. We have them here as well as the WRI, Water Research Institute. So before we put the Gans on, we calibrated the what do you call it, the skills, in order to be sure of what we are putting on.
Hello, Benjamin. Am I muted? Maybe he is off when he comes back on. It's till we get Benjamin back. Are we back again?
We are back. Yeah, I'm back. So
Go.
we we tell the what do you call it, the weight, and then it got to 0 0 before putting the Gans on it, and our target was to get 0.10 gram. Okay, 0.1. Okay, gram of the Gans in order to use it. So we got the Gans, and then we proceeded to the next step. Please, the next step. The next step was to preparing the treatment solution. Okay, so we have the Gans here. And this is the concentration, the formula for the concentration. That's concentration is equal to mass over volume. Okay, so we took this amount of weight and then 10 ml of water, distilled water, and then we diluted it. We diluted the substance, and then that was it. That was it. So it that is what you see. The solution has been prepared. That's what you see in my hand. Please, the next slide. Okay. So our next instrument that we needed to work with was this one, the sense ion 156 multiparameter. And this easily measures the pH, dissolved oxygen, total dissolved solid, conductivity, salinity, etc. We needed to be sure of what you are doing. So the old battery, which was inside, was removed. We put a new one because we wanted to be sure of, and then we calibrated it to the default, what do you call it, factory settings before we started using it again. And that is what you see, the pictures that you see over there. I did it with SADA. Uh, okay, let's move on. The next one. And in order to ensure that our processes are clean, we needed to do a lot of cleaning and sterilization of the bottles that will be used. Okay, so we clean and clean it again, make sure that it is properly disinfected so that we don't introduce any foreign matter into our treatment processes. Okay, so we move to the next slide. That's what you see, the pictures, tubes that you see over there. And in order to prepare for the treatment, we have to label our treatment bottles or tubes. So as you see, these previous, you already know them already. I've uh, discussed with you pra, ofin, and brim. The one that you may not know is the Odumasi one, which is giving us a funny kind of results we will share with you. Okay, so the next one. And we took 50 ml of the water from each of the listed river, and we tested them on various parameters immediately and after. Immediately we put them in, we put the probes in to test for the parameters we are looking for. These are common parameters that is looked for in treatment of any contaminated water or water that is polluted. So we tested these ones first, and then after introducing the Gans solution, 1 ml, that's 1 ml of Gans solution in the water, just immediately after introduction, we, just immediately after the introduction, we agitated the uh, uh, tubes in order for the things to mix properly. Okay, and then we tested the uh, water immediately. Okay, the next one. This, as you can see, this is the treatment of the water after 24 hours. It is well settled. The sediment have settled. Uh, Even the the offin, which was so polluted, has settled well. And then you can see the sediment, that is settled under the brown ones. The one that had a lot of sediment was the offin. Okay, so the next one. And I will hand over that one to Sada for the analysis, because That is his field, and Nash is also here. I conferred with Nash with the results. When I did that with Sadatu at the Water Research Institute, I came back and we did conductivity over uh, total dissolved solid over conductivity, and we found out that it was within range. Zero, all of them were hitting the range 0.5 to 7. It must fall within this range. Otherwise, your water is not good. Okay, so it was on the mark 0.5. All of them were exactly on the mark. Okay, so I'm handing over to Sadatu for Sadatu to get on with the explanation of the results, which you can see in there.
Hello. Actually, we started this work some time back. As he rightly said, he did a treatment on his own and brought a raw water sample without treatment and another treated with a Gans. The problem we realized was that there was a lot of ion introduction. So there was a lot of the conductivity was very high when when you analyze the treated water, which is not supposed to be so, because like we are introducing more ions into the water. So that was what informed us on what to do. So we realized that the first step to take was to check salinity, since in the process of preparing the Gans, salt is introduced. If salt is introduced, it means ions are introduced. So you actually expect the conductivity and the ions to be very high. So what we decided to do was to take the raw sample, then use the probe to check conductivity, dissolve solid, and apparently the salinity. And that is the raw one before we added the nanomaterial or the GAN, so that we can be sure of the interaction between the GAN and the samples, whether we are introducing more ions or now the GAN are okay. The actual precaution we took was Benjamin had to wash the GAN several times to see whether we can actually remove the ions. So the salinity. So what we actually did was, after adding the nanomaterials, we took the results again. Immediately we added the material, we agitated it, and we took the readings so that we can report immediately we added and after 24 hours what we observed. So when we added the material immediately, we observed that with some of the water river bodies, the water, the conductivities were going a little slightly up. Others too came slightly down, but mostly the difference were not significant. And after 24 hours, we also decided to take readings. And the readings, it was not, there's no trend. For now, we can't say there's a constant trend. It depends on the water, the river body. So mostly the conductivity, if the conductivity goes up a little for one, the salinity we're still recording salinity of 0. But with other ones, like the Ofin,
Please.
the conductivity went up a little after 24 hours. And we're
Pardon?
recording, hello?
Yes, we need Rick to enlarge the screen. We don't see the data. Rick, is it possible for you to enlarge data we can see?
Yeah, maybe I can do that. Let's try that.
Please. Because she's talking about the figures and data we have no clue about. We don't see it. Can you enlarge it furthermore? A little bit more? Okay, just, yeah, that's about right, yeah. Okay, sorry about that. Can you carry on, please?
Okay, so when we take the raw sample with the PRA, the conductivity, we're getting a conductivity of 211 microsiemens per centimeter. And the total solid was 109 milligram per liter. But it was recording a 0.00 salinity, meaning that with the raw samples, we're not having any salinity problem with it. But with what Benjamin was trying to explain to you, with the Odumansi we were recording a salinity of 0.2. So we wanted to see what would happen after we add the nanomaterial or the GAN. So after adding the nanomaterial, we realized the PRA was still giving us around 214, which is just around the same as the raw was giving us. And the Odumasi, which was a little different from the rest, was giving us 421 microsiemens per centimeter, which is also, if you are looking at in terms of figures, you can say that there is about 25 difference. But in terms of salinity, we realized that the salinity dropped to 0.1. That is immediately after adding the GAN, the GANs. So, but after 24 hours, the conductivity rather was down, which was 379, which we recorded, and the salinity was 0.1. So we concluded that, meaning that this time around, we've been able to be lucky, and the nanomaterial is not concentrated, is not contributing salinity to the particle, to the water that we are treating. Because in treatment, we have to be careful what we are introducing to the treatment material. If not, we would think we have treated, and still, when we do other reactions, we can't use the water because we would have introduced other foreign things which will not be. To be sure of what we're doing, we started with 500 ml, so that we can calculate the actual concentration. Actually, when we are doing treatment, we want to use a very concentrated sample, and so that we can use a small quantity and we can be able to have a bigger effect. I think that was what we were trying to see whether we can achieve that. And so far, we'll say yes. With the 15 ml that we used, with 1 ml of the prepared solution, we're able to achieve that. But we can't conclude on this because the volume is too small. When it comes to treatment, we deal with a very large volumes. So in this case, it means we have to go further and do other studies. But the interesting thing is that we try to do microbial load and other things so that we can actually know whether, if we put the GAN aside, maybe making the water clearer or purer or treating the water, what does it do to the microbes, whether we'll get them, so that we can use the same thing to work for both. So we try to do some analysis of the water we treated and the water we did not in terms of microbiology. Thank you.
So we'll continue with the next slide. Please, can you roll the next slide for us? And I think that is for Bobo to come in. And then, because, hello? Hello?
Hello, you're there.
Yeah.
Don't worry.
We're hearing you. I just got to make it
Rick.
smaller now so we can see. Just a minute.
Hello?
Yeah, I'm
Okay.
here. Hang on.
Uh-huh.
There
So,
we go.
like Sada rightly said, we need to know, because after the normal in the alum in to clear the water, it need to be chlorinated and so on and so forth. So we needed to be sure of what the GANs would do to the microbial load inside the water, and that was our next step. And over this week, this was, you can see the date, 16th May 2016. This is the news, the latest news. Ghana Water Pro research scientists clash over water safety. That is what is on the news, because there's one section, there's a river which pumps water to one section of the city, and it is loaded with microbial toxins, and they don't know. The treatment unit is saying that the water is safe for drinking. And Sada's institution, a researcher there, has found out that the water is not wholesome because it contains algae toxin. that is HBA, harmful algae, blooms, in the water. So, and these things the water may look clear, but with time, as you one continue to drink this water, it can accumulate in the body, part like the kidney, the liver, and then the nervous system, and then one may end up, getting sick or even lose his life. So it was an interesting angle that we decided to look at the microbial, the effect on microbial load. And I know for sure, but they want to be sure. I know that what I have in my hand, the Gans can deal with any kind of virus. Okay, so that was the next slide. That was the next, what do you call it? The step that we took. Please. So the answer to this is the plasma technology, solution, and understanding, like Mr. Kesh rightly wrote in the viruses and bacteria paper, understanding the property of the matter of the gans and their interaction. Gans can be used to influence the state of a virus because viruses are maggra-based entities. Thus, they have gravitational and magnetic field. So, if you know how to, apply it properly, you can transmute the virus and then deactivate them or make them, ineffective. You know. And yesterday, I was sharing with a lady who had problem issue with some pains, and I was recommending vitamin B12 and B9, because when these viruses are in the body and you take these vitamins, they're able to, deactivate them or reduce them to their saline state so that the body can, pass it out, as urine or any form of fecal content or sweat. And then one is free from. So understanding this technology properly, will go a long way to help us, solve our many-sided uh, problems. Please, can we get to the next slide? So I'll soon hand over to Bobo for him to do the microbial analysis parameters. These are 4 parameters he chose to analyze, and these are common things they do, and these are, things that are normally hidden in the water. Total coliforms, TC. So when you see it in the pictures, you know what it is. Fecal FC, and then Escherichia coli, E. coli. That's what we call E. coli, and heterotrophic bacteria, THB. So I'll hand over to him this time because I will not do the work of an expert. He is expert in his field. So,
Hello. Um, we after the work on the water, after the physiochemical test, we did microbiological tests as well because you cannot say if the water is physiochemically safe and uh, is safe for drinking without doing the microbiological test as well. So we did some of the indicator bacteria to see whether the water is safe. Indicator bacteria are just bacteria in the water. They don't show the presence. Their presence in the water shows the presence of other harmful bacteria in the water. So we chose to do total coliform, fecal coliform, E. coli, and total heterotrophic bacteria in the water. Next slide, please.
next slide.
We do membrane filtration on the water sample. It's just a simple analytical method to identify the bacteria in the water. It is simply filtering the water through a membrane filter paper, which is 0.45 micrometer pore size, and bacteria molecules are quite bigger than 0.45 micrometer. So what happens is that the water molecule passes through the membrane filter, trapping the bacteria molecules on the filter. After that, we put the filter on a nourished nutrient or a prepared media, and incubate at appropriate temperature for it to grow. So after that, we read the colonies under a colony counter, as you seeing. That's a sample of a colony counter there. Next slide, please. Okay. After incubating in appropriate incubators, this is a sample of the results you are seeing now. This is a fecal coliform of one of the rivers, that's Birim. So you see the Birim raw and the Birim treated. You can see the raw has got colonies on it, and the treated has got nothing on it. That shows that the Gans are working in the treatment. Next slide, please.
Excuse me, before you go to the next slide,
Okay.
can you hear me?
Yeah, I can hear you.
What have you used on the right-hand side and what is on the left-hand side? Where we see the colony.
Yeah, the left-hand side is the raw sample, and the right-hand side is the treated sample. That is the raw sample you're pointing to.
Okay, what have you treated this water with?
After they've treated with the Gans.
So the
after treating
treated
with
water on the side, is it the treated with the Gans water which you measured at the beginning?
Yes. Yes, the one at the right side is the one treated with the Gans, and the one at the left side is the raw sample.
Okay, thank you very much. Okay, can we go to the next slide, please?
Yes.
Okay. Hello?
Okay. Yeah, hello. Please, can you go to the next slide? Okay, the first one was a fecal coliform. This, we are seeing a sample of a total coliform and E. coli. We use a chromogenic media, which is a high chrome coliform mega. It is a media that selects total coliform and E. coli. You can differentiate it by color change. You can see the total coliform being salmon red or pink, and the E. coli being blue. If you zoom in very well, you can see them. And the sample at the left side is the raw sample. You can see the quantity of colonies there, and compare it to the one at the right, which is the water treated with the Gans. You can see that the amount has reduced drastically, though it's not 100%, but the reduction was quite significant.
So the right-hand side is treated with less colonies?
Gans.
With the Gans.
Yes. And
is that with the less colonies or less effective colonies?
Less colonies.
Okay. Why some of them are so large on the right-hand side?
Oh, because the colonies are not much on the media, so they have more nutrient to grow. And the one on the left hand side, they are much, so they have a limited nutrient to grow. That's why you see some of the colonies big on the right hand side and some small on the left hand side.
Yeah. Next slide.
Next slide, please. Internet.
Okay.
And this a sample of the colonies we do. This total heterotrophic bacteria. It's not so clear here, but on a slide you could see the quite difference between the raw and the treated sample. And if you go to the next slide, you see the numbers, the results, and you can compare the numbers to it. So next slide, please.
Okay, we got the figures now. Can you open it a little bit, please, Rick? Okay, thanks very much.
You can go to there's another. This is the result. report, you can go to the next slide and you will see the actual figures. Please,
Go,
next slide,
can you
you will see
go
the
to the
real
next
figures.
slide, Rick, please? Go up, please. Okay. Is that good?
The next one.
Please go to the next slide. You see it quite clearly there.
Is this the slide you want?
No, the other one. Okay, this one.
This one is quite clear.
Okay. Can you explain to us, please?
Okay. This the samples are the river samples, and we did the total coliform, as I said earlier on, the fecal coliform, E. coli, and the total heterotrophic bacteria. And we have standards, standard in Ghana we use, and we compare it to WHO standard as well. The standard in Ghana is for the total fecal and E. coli is supposed to be 0, but for the total heterotrophic bacteria, it's supposed to be less than 500. So for often the raw sample from often, you can see the values there. The raw sample is reading 166 for the total coliform, 50 for the fecal coliform, 46 for the E. coli, and 3,744 for the total heterotrophic bacteria. When you compare it to the treated with the Gans, you could see reduction to 13 in the total coliform, 0 in the fecal coliform, 0 in the E. coli, and 114 in the total heterotrophic bacteria. And I tried calculating the percentage efficiency of the Gans, and you could see the efficiency of the total coliform for often for the total coliform is 92.16%. For the fecal coliform is 100%, the E. coli is 100%, and the total heterotrophic bacteria is 69.44%, which is quite encouraging. And you can see it ran through all the other rivers as you see down. So if you take example, you take Brim. If you compare the treated to the raw, you could see that there's a reduction in bacteria, though not total reduction, but there's a reduction in bacteria in it. And if you calculate the percentage efficiency, you can see there's quite most of them are more than 50% in treatment. Next slide, please. So I give some few remarks. The surface water sample, they were subjected to the Gans as stated. The level of the contamination are showed as in the table above. Bacteria counts were significantly reduced, as you see in the table, and the Gans show marked efficiency in reducing the bacterial colonies in the water river sample. So next slide, please. And I also gave some few recommendations. I realized that though there's reduction, there's no total reduction in the bacterial colony. So what could be done is the Gans could have worked better if you use less polluted water, or example, borehole water or well water, which is not as polluted as the river.
Hello.
Oh,
I think
hear me?
we lost him
Rick?
briefly.
Can you hear me?
I can hear you, Mr. Keshe, yes.
We just gotta wait till they come back. Most probably they're on the bathroom. We just wait for it. Just till they come back. Do we have any scientists in the background who can discuss this with us online? Where and how we can use if we go back to the data which we've seen. There is a couple of points I think we have to raise when they come back. and we got to see the data, and we got to go back to see the sediment in what it was. You're back?
Hello? Yeah, we are
Okay.
back.
Okay, let him carry on, please. Go back to where we were.
Um,
Your
okay.
recommendation.
Yeah.
We are under your
Okay.
recommendation.
Yeah. I realized that though there's reduction in bacterial colonies, there's no total reduction in it. So if you use less polluted water than the river water sample use, there may be improvement in the reduction of bacterial colonies. And if you want to use the more polluted water like the river samples use, maybe the concentration of the Gans should be increased. That will show marked efficiency in the treatment process as well.
Can I come in and maybe make a recommendation or a suggestion? This
Okay.
is added to the knowledge since you've done these tests. We have moved in our technology from the using the Gans to use the Gans water, which means you don't need to hold the Gans inside. You mix the Gans with the water, and then you take that water to see how effective it works. So it means, for example, when you treat the water, people would not consume Gans anymore. And the test in Tokyo shows us that the Gans water is as effective as the Gans itself. So if you could do a test like what you did with copper oxide, you can add as much as you like the water of the Gans without any Gans and see if you get the same result. So if you use it for water treatment, you don't need to keep on producing Ganses to add. You just create a bed of water.
Use the water.
Yeah, and that the water gets mixed up with the Gans, and you just take the water and you can just add it naturally to the water process and disinfect the water in natural way. There is something which is again come up in other researches which is important, is that what about if you reduce the amount of the copper oxide gas water and you increase the CO2 gas water? You don't want to kill all the nutrition in the water. Copper oxide is a punch, is a sledgehammer. Is there a possibility that we could see some data using, because you released this before, about a couple of months ago when we saw the research from Atomic Energy Lab, that CO2 was less effective. But is that the compromise we need for the rivers to kill the bacteria in a level that's not harmful, but enough to allow fishes and the other animals to live in it? So there are 2 points for the water authorities. Then, in a way, you can just make stations across the river where you just add water to it in a composition which allows the fish to grow, but not the bacteria to exist. So is it possible to take a next step research on to see, don't use the gas? Because in the slide you showed us, we see clearly the gas powder at the bottom. And this is itself a source of continuous existence of material you don't need. But would it be possible to test not just the water and we see some data? And if that can be done, the nation doesn't need to keep on buying copper to produce copper oxide. You produce it once and you can use it for years and years. Is that possible? Could you do such a research for us?
It's possible.
Thank you very much indeed. Carry on, please. Do you want the next slide?
No, there's no. This is the end of the, what do you call it? The slides. You know, I don't think we have any more. That's the end.
Thank you very much indeed. Thank you, the scientists in Ghana Water.
But Mr. Kesh, Mr. Nash is here. He's hiding from you. He doesn't want to talk.
Pardon?
Nash is here.
Dr. Nash.
Yeah. Nash is here. He's holding your sediment, so you attack him from here.
Pardon? It's hiding from. No problem. Thank you very much, Dr. Nash, for being there. Thank you for all the facilities you made available to Benjamin that we can bring the knowledge. It's important. What is very interesting when you look at these pictures which you showed us, the videos, what you call the images, we see the wrong image of the man most of us have about Africa in some places. We see some of the most sophisticated equipment which is available in the West. We see highly competent scientists who can use it. And this is very important. It's not that something is done and we can't accept. It's something done in a worldwide standard of evaluation of the knowledge. And we see the latest machinery, the highest caliber of scientists humanity can create. In a way, we thank you. And if you can bring the knowledge to share it with us, furthermore, that we can carry on, we give you any time you want to come on the presentation to present to us. You have to understand what you just shown from Africa has been seen by world leaders, by people who are influential in every aspect of life. And I think, as I said, you set a standard for the others to follow. This brings, in a way, data scientifically to show that the Gans water or the Gans itself can be used as disinfectant, can be used in controlling infections. But now, this is the beginning. This is what I call the first shooting of the bullets of the knowledge in use of Gans for the rest of the scientists to add to it. We see more of these to come up, and I thank the scientists in Africa, the water authorities, and the Atomic Energy Commission of Ghana that has made Ghana the focal point of the plasma technology, which very simply, with no cost, literally little cost, you can change a lot of things, you can save a lot of lives. You see in the Ebola, we see from Ghana, what they call Sierra Leone South University, the effectiveness in Ebola and E. coli. We reported this over a year and a half ago. And the threat which was made on the scientists by World Health Organization to keep them silent, with what you put on the picture, confirms their work. I think if you talk and start collaborating with the scientists in South Sierra Leone University, they will join you. They have a lot of data that they could help you to add more to the knowledge of African nations. The results has been tested in China. We know the results has been tested in US in laboratories. We have some information. And so in a way, what you put on the scene, what you put on the screen allows us, is encouraging enough to go further to find out that we don't need, do we need the Gans of the material? Can we use the water? Because the water of the Gans looks to be as effective of the Gans itself. We know it works. TEPCO in Japan is using it heavily, the water Gans, for the contamination of radioactive material. It would be nice if the water authorities, you scientists in Ghana Water Commission, could collaborate with the scientists in Ghana Atomic Energy to test radioactively contaminated water. And let us know by adding the Gans how much is reduced. How much? If the way you measured it now, you can let us know. You used powder of the Gans. If you would have used the liquid Gans without powdering it, you would have had totally different result too. The powder gives a different effect. So if you would like to test Now you know roughly this much Gans roughly has this much value or this much weight of Gans in it. Don't dry it and test it directly. I'm sure you will see totally different result, more effective. We know this from other researchers. On the other hand, if the collaboration now you can go back to Ghana Atomic and then mix some of these river waters with radioactive material or plain water with radioactive material, and then add the Gans or water of the Gans. Then you can tell us how effective Gans can be used for decontamination. This is very important. And then this will open a lot of things the way what we achieved in Fukushima with TEPCO. They seal the books. Maybe you can show the effectiveness of it through Africa, that other countries like America with the power station, nuclear power stations, when they run into problem, they look into Africa for solution. You become the heads of the research in nuclear atomic contamination. You have the facilities. I know what you use. I have a good understanding of what sits with the atomic energy authorities in Ghana. And it'll be fantastic that the freedom we have now in Ghana, can we test the effectiveness of CO2, copper oxide in contaminated, radioactive contaminated waters and see how it will diminish or reduce it. We know the data, we know it works 100%, but if you can produce us a second report with this, like this, what you've done scientifically, we cannot put a pen in it or a pin in it to say there is something wrong, then Ghana Atomic becomes one of the leading organizations in the world heading plasma in decontamination on an open basis. Thank you very much, Benjamin, for such a beautiful presentation. Thank you, the doctors and the scientists in the Water Authority. And I hope this will be the beginning of sharing knowledge with us, the way you see it.